Imagine pulling into a station, and instead of waiting 40 minutes for a charge, your car's entire floor is replaced in the time it takes to check a text message. This isn't a science fiction concept. It is a logistical masterpiece occurring thousands of times every single day. The scale is staggering. In a single 24-hour period, this network successfully completed over 146,000 battery swaps. That is not just a triumph of logistics. It is a testament to mechanical engineering operating at the absolute limit of precision. But the real magic happens out of sight, beneath the vehicle. A hidden world of high-speed robotics and specialized fasteners works in perfect synchronization to perform a task that would take a human mechanic hours. When you drive into the bay, you aren't just parking, you are docking with a high-precision computer. The system uses ultrasonic sensors and cameras to align the car within millimeters of the target zone. Once the car is locked in, the floor opens to reveal the battery swap platform. This isn't just a lift, it's a mobile laboratory equipped with its own intelligence, ready to perform a surgical extraction. The challenge here is immense. The system must handle different car models, varying weights, and the unpredictable debris of the road, all while maintaining a sterile level of mechanical accuracy. The secret to the speed lies in the bayonet bolt system. Unlike the bolts on your wheels that require many rotations to tighten, these are designed for rapid engagement and extreme durability. Every battery is held in place by 10 of these specialized bolts. To meet the 3-minute goal, the system doesn't unscrew them one by one. It attacks them all at once with a synchronized robotic array. This synchronization is critical. If one bolt is removed faster than the others, it could tilt the battery pack, causing it to jam or damaging the sensitive electrical connectors. It's a mechanical ballet of perfect timing. Beneath the station floor lies the battery bank. This is a climate-controlled vault where swapped batteries are stored, inspected, and charged at optimal speeds to preserve their long-term health. As soon as a depleted battery enters the bank, the system performs a diagnostic check. It looks for thermal anomalies, physical damage, or any signs that the battery needs maintenance before its next journey. This centralized charging is far more efficient than individual fast charging. By charging batteries slowly and in a controlled environment, the network can actually extend the life of the cells compared to traditional EVs. But why go through all this trouble? Why not just build faster chargers? The answer lies in the physics of energy transfer and the limitations of our current electrical grid. Charging a battery in 10 minutes requires a massive surge of power that can strain local transformers. Swapping allows the station to draw power steadily throughout the day, acting like a giant sponge for the grid. The engineering challenge was to take a complex manual process and turn it into a reliable automated service. And the key to that reliability is the high-speed robotic wrench system. To understand how the swap works, we have to look at the RGV, or Rail-Guided Vehicle. This is the robotic platform that lives under the station floor, moving with sub-millimeter precision to find the car's hardpoints. The RGV uses a combination of laser rangefinders and visual odometry to lock onto the vehicle. It doesn't just guess where the bolts are, it sees the undercarriage in 3 dimensions. Once aligned, the RGV raises the battery tray. This isn't a simple hydraulic lift, it's a multi-stage telescopic system designed to maintain a perfectly level surface, even if the car's weight is unevenly distributed. Now let's talk about the wrenches. These are the stars of the show. Each station is equipped with a high-speed E-wrench array that can spin at thousands of RPMs while delivering precise torque. Unlike a standard air impact wrench, these are fully electric. This allows the system to monitor the exact torque curve of every bolt. If a bolt feels too tight or too loose, the system knows instantly. The bolts themselves are a marvel of metallurgy. They must be strong enough to hold a half-ton battery during a high-speed crash, yet smooth enough to be unscrewed in seconds without ever seizing. Synchronization is the hardest part. The system must coordinate 10 different wrenches to move in perfect harmony. Think of it like a 10-fingered hand unscrewing a lid. If one finger moves faster, the lid tilts. To achieve this, the station uses a real-time industrial controller that communicates with the wrenches every few milliseconds. It adjusts the speed of each spindle to ensure the battery lowers perfectly flat. This level of control allows the system to remove the battery in under 30 seconds. It's a blur of motion that looks simple, but requires millions of calculations per second to execute safely.